What's up, guys? This is Mr. K. Wanted to make my first and probably last calculus video. Today I'm going to show you the next lesson, which is how to find the volume of a solid that results when you take a shaded region and revolve it around a line. We're going to start by revolving it around a really simple line, the x-axis. So you can see here they give us a function. They give us y equals 0, which is the line right here, and they give us these two horizontal lines. So they give us a clear region right here. Okay? We're going to take that and we're going to spin it around the x-axis. So if you could imagine this thing spun around the x-axis, it looks like this point will end up here. This one looks like a little bit like 2.2 or something. It'll end up at negative 2.2. It'll spin around this end spins around like that, and you end up with a 3D object. And this end will look like that. If you can imagine this whole thing spinning around, you create what looks like, I don't know, a sideways, kind of like a cereal bowl or something. So we're going to take that and try to figure out the volume of it. So remember, when we do this, we're splitting this up into a bunch of little discs. That's why it's called the disc method, or a bunch of coins. So if you look at this, let's look at this coin first. This is the face of a coin right here. There's an infinite number of those getting smaller and smaller as you go down this way. So if I find the area of that, I can find the volume of the cylinder. Okay, so before we start doing integrals or anything, let's just look at this coin. This coin has a radius that's like that, and that's all you need to find the area of it, right? So let's write that. The area of a circle is pi times the radius squared. And now it's really a cylinder. Remember, it's a disc, so it has some sort of little depth here, okay? We're going to assume this coin has some depth, and the depth is getting closer and closer to 0 because we want the number of discs to be infinity to get a really accurate volume estimate. So we're going to multiply by the width, how high the cylinder is, and that would be dx. Remember, for really small changes in x, we could just call it dx. Okay? So you can see eventually, if there's a dx, we're probably going to be integrating something somewhere. But hold up for that for now. This radius right here, how do we find this radius? Well, it looks like it's from 0 to whatever this number is. Now, I could tell it's 3, but in general, it's going to get smaller as you go. This radius is still part of this shape, but it's a little bit smaller. This radius here is part of the shape, but it's even smaller. So the good news is, to find the radius, it's just the value of the function at all those points. The value of the function is just the function. Here it is. So if it's revolved around the x-axis, it's real simple. The radius right here is always just the value of the function, whether it be f of x or y or whatever they call it. And of course, we're going to square it. Green for St. Patrick's Day. There we go. We're going to take it and square it. So let's write what that looks like. The pi is still there. The radius is the function. Take it, square root of x plus 2. And we know area of a circle is pi r squared. So I need to take the radius and square it. And of course, since it's a cylinder, multiply it by the height, or the width when it's standing up like that, which is dx. Now we see we have dx. Clearly, we don't want just one of these discs. We want every single one of these discs in this volume. So I'm going to take it. Remember, if I'm adding up a bunch of infinite sums, then I'm taking the integral. So next step is just to take the integral. Now, from what to what? Good question. The volume, the shape starts here, right, which is at 3, and ends here, which is at, can we cover it up? Looks like 7. So I'm integrating from 3 to 7 of this function right here. Pi square root of x plus 2 squared, and then, of course, dx, since I have an integral. That right there is a perfect setup. You could show me that, plug that into the calculator, get the answer, and you'd be good. That'd be it. But since this is such an easy function, I could already tell, I'm just going to hand integrate this, and it's going to be super simple. Check it out. Use red. Why not? All right, so I'm going to pull the pi out, first of all, because who needs it? It's a constant, so I can pull it out. 3 to 7. Now, here I have a square root of x plus 2, but the whole thing is raised to the squared. So those are inverse functions. They just cancel out. And all I have is x plus 2 dx. Super simple integration problem right here. Definite integral. So I'm going to take the antiderivative, plug in, take the antiderivative and plug in 7, plug in 3, and subtract. Bada bing, bada boom. Let's do it. Purple. Okay. Antiderivative of this, that should be pretty easy. I'm going to leave the pi out front. And I'm going to, antiderivative of this would be, let's see, x, raise that to x squared. Old coefficient divided by the new exponent, 1/2, plus 2. Remember, antiderivative doesn't go away. It becomes 2x. And, of course, I want to, boop, to my notation, plug in 3, plug in 7. Again, I'm leaving pi outside. I'll just bring in pi at the very, very end, and I'll be good. Now, this should be super simple for you. Just plug in 7, plug in 3 into this function. Leaving pi out front. I have 1/2. X squared is, let's see, first 7 squared is 49. So I'm just going to change this to 49 over 2. Plus 2 times x, plug in 7 is 14. Minus, now I'm going to plug in 3, exactly like I plugged in 7. Parentheses, 3 squared is 9, so I get 9 over 2. Plus 2 times 3 is 6. Cool. I put the parentheses so I would not forget that this negative does need to be distributed to these. I could distribute it right away, but let's be honest. We're probably going to forget if we don't. All right. So pi, still hanging out front. Great. Awesome. We got 49 over 2 minus, use a highlighter here so you could see what I'm talking about. 49 over 2 minus 9 over 2. Well, that's easy. That's 40 over 2. Cool. Common denominators. Sweet. And then I have positive 14. This looks like a plus 6, but remember that negative is going to distribute. It's a minus 6. 14 minus 6 gets me 8. It's a positive 8. Cool. Now, so let's see how these is. 40 divided by 2 is 20. 20 plus 8 is 28. I get 28 pi. That is the answer, and that represents the entire, the entire volume of this solid shape, which is like a ceramic bowl, for those of you in ceramics class. See it? 28 pi. You can get the decimal if you want, but this is fine. This is the exact answer, and this right here was the exact setup. This right here was the exact setup. Both those things will get you a 4. Let's see, where's my, there it is. So there is a formula. It's right here. Nope, don't do any of that. Okay, here's the formula right here. I can't annotate this page, I don't think. Nope. But this, if the shape is rotated around the x-axis, this formula is right here. It's basically pi r squared, pulled the pi out of the integral. And we're adding a bunch of those discs, so it's the integral of the radius squared. Remember, the radius squared is just y squared. Okay, that's f of x squared, the function squared. Got it? But memorizing the formula, it might help you, but it's best to look at the actual function. Think about the discs. Imagine them, because sometimes the radius is different. Down here, it shows the shape rotated on the y-axis will be this. Stay tuned for the next video, and I'll show you how to do that. But for now, this is a good start. Okay? Next video, we'll talk about rotating around the y-axis, like number 2, as you can see right here. And then after that, we'll talk about what happens when you don't rotate around an axis, you rotate around another line. But we'll talk about that in the future. Thanks for tuning in. Hope this helped. And don't forget to smash that like button. Thanks.